Okay, so question one is on the screen in front of us. It says a diagram shown has a 2 meter tall object. It's positioned at x equals 10. It's in front of a concave mirror at x equals 14. And there's a focal length of 3. What we're asked to do is to draw the 4 principal rays and use those 4 principal rays to kind of figure out where the image ends up. And then we're going to do the exact same thing, but instead of proceeding graphically, we're going to use the mirror equation and do everything with equations and algebra. And class remark there says that everything should agree. So one thing to keep in mind that's important with questions like this is that we're kind of given positions. And we have a number line. This is kind of all overlaid on a graph. So we have a y-axis, an x-axis. The units on each are in meters. But the thing to keep in mind, you guys have seen now in lecture, right, that quantities like object position, image position, focal length, stuff like that, those are quantities that will help us when we end up doing using algebra and equations. But these are always referenced with kind of respect to where the optical element, such as the mirror or the lens, as you'll come to see in subsequent lectures, where that's positioned. So for instance, even though it says the object is located at x equals 10, this is what we define as the object distance. It's located at x equals 10. The mirror is located at x equals 14. So this distance to s is actually 4 meters. So that's just something we have to keep in mind. So if we want to use the equations, the mirror equation, we need to kind of use this coordinate system. And at the end, we want to kind of say where things occur on the line. We need to convert back to what this is with respect to where x equals 0 is. So the first thing we want to do to help us with our principal rays, we're told that the focal length is 3 meters, so let's label that. So when it says 3 meters, I kind of just mentioned, it means 3 meters from the mirror, so each grid space is 1 meter, so we just want 1, 2, 3 meters to the left. So this point here on the optical axis, that is our focal point. And one thing that can also be helpful to label now, while we're here, is the radius of curvature. That's just twice the focal length. So 1, 2, 3 takes us out 6 meters this time from the mirror, double, and that's the radius of curvature, capital R. So now we're all set to do some ray tracing. So I'm going to try and do these as accurately as possible. Kind of the program I use and the trace is not always perfect. So get something that's slightly different from the calculation, then maybe that's just due to the fact, or it should be due to the fact that my drawings are not perfect. But I'm going to try my best. So the first ray that I'm going to draw, this is going to be incident from the left. I'll put arrowheads on it in a second, but it's incident from the left. It's parallel to the optical axis, and we draw all of our principal going through the top of the object. That's the tip of this arrowhead. So a ray that is parallel to the optical axis, it reflects from the mirror and goes through the focal length, or the focal point. So something like this, I guess. And we'll draw this, it's pretty handy. Just draw this line to the limit of the graph because we don't know what it is. We're going to draw the next 3 rays and we're going to find out where they all intersect. So it could intersect at x equals 9, it could be all the way at x equals 2. So it's good just so we don't have to go back and draw. Draw the lines very long, I guess is what I'm recommending. So we'll change colors maybe. Do a few so we can keep which line is which straight. So the next one, there's no real order to have to proceed in. You just have to get all 4. The next one I'm going to draw is from going through the tip of the object, as always, incident on the mirror where it meets the optical axis. So something like this. Incident kind of at the optical axis, the center of the mirror. You can imagine this is coming in from the left and down, and the law of reflection kind of says that this has the same angle, like this. And for the sake of understanding the process, we're going to do all 4 principal rays, but at this point you can see that the intersection is over here already. So theoretically we're done. We can already draw the image based on this. We're going to proceed onward just to make sure we have full coverage. Let's skip green in case anyone's colorblind. The next one we can do is one that passes through the tip of the object, through the focal point or the focal length, and then is incident on the mirror. That was kind of hard to draw, so I'm just going to start there. That's going to intersect the mirror. And one feature to note when you're doing this, let's switch back to the pen for a second. This little bit of curvature here, the thing that if I blew it up, it looks like this. This is just to denote that this is a mirror that is concave in this direction. But it's just kind of a correct way to say it. It's just kind of a notation in how this is drawn. We consider this mirror to be very flat and very like approximately flat. So this is, I'm drawing this all the way to the edge at x equals 14 where this mirror is. So I'm going through this point. So this is just kind of stylistic. We assume the mirror exists only at x equals 14, hence why I'm drawing it right down to the corner there. Hopefully that made sense. If it doesn't, just make a note in the chat and I'll try and go over it in a new way. So yes, this one bounces off at x equals 14, like I said, and if you pass the focal length, the rule is the reflected ray is parallel to the axis. And our final one, let's do cyan, is kind of a freebie, or it's the most simple. A ray that passes through the tip of the object and the radius of curvature, it actually reflects and goes back the exact way it came in. So I did a pretty bad drawing that. Let's see what how I undo this. Maybe that's a bit better. And then we can go back out. And we should also end up at x equals 2. Or yeah, so that's a bit better. You can see how, as I'm kind of, even with a program that automatically draws straight lines, how if you kind of are just off by a tiny bit, it can affect your final results. That's another kind of good reason to do all 4 rays, because if you had 2, you might get it slightly off. Suppose your second ray doesn't agree with the other 3, you can kind of figure that out if you do all 4. If you get lazy and you only do 2, you might not get the answer exactly right graphically. We are going to do this algebraically as well, so we'll kind of have verification on top of that. And just in case it wasn't clear with these, I'll label kind of which direction the light is going. So the red, the first one, just to recap, is an array optical axis that reflects through the focal point. The kind of equal but opposite or same idea is a ray that goes through the focal point, and when it reflects, it's parallel to the optical axis. A ray that's incident at the center of the mirror on the optical axis just kind of goes or reflects at the exact same angle. You can kind of see here, we have this angle and this angle are the same. And a ray that is incident through the radius of curvature reflects and then goes back along the same trajectory. And these all overlap right here. So we can draw our image. So our image is bigger and it's inverted. It's pointing below the x-axis where the other one was small, pointing above the x-axis. That's a really bad drawing now that I'm looking. There, a little bit more at x equals 2. So now we need to do this with the mirror equation. So the mirror equation is that the reciprocal of the focal length is equal to the sum of the reciprocals of the object and the image positions. So what we really want to solve for is the image position, we have the information for the object, we have the focal point or the focal length. We'll solve for S prime. So the first thing we can do is move the 1 minus S over to the left side. We can cross multiply on the side. That's how you want to think of it. Now we just have two fractions, one on it is Fs over S minus F is equal to S prime. So now we're ready to plug some numbers in. What is S? We said S was 3, no, S was 4 meters. The object was positioned 4 meters from the mirror. The focal length was 3 meters. It's divided by 4 meters minus 3 meters. So the denominator here is 1. The top is 12. So we just have 12 meters. And then I'm not going to go back and actually convert this, but we can kind of look here. Our drawing said that we were positioned at x equals 2. Our mirror is at x equals 14. The difference between 14 and 2 is 12. So that checks out. We can figure out, we can either compute the magnification from the image height divided by the object height, or minus the image divided by the object distance. If we ignore the magnification for a second, and we just work with kind of the 4 quantities here, we have S prime now, we have S, and we have H. We'd like to figure out, remember we're located magnification for kind of the algebraic parts. So if we want to get the height of the image, that equals minus the height of the object times S prime minus S. The initial height or the object height was 2 meters. The image we just found, the image position was 12 meters from the mirror. And 4 meters. This fraction on the right is 3. The initial height or the object height was 2. So this is minus 6 meters. This makes sense. The minus, all this means is that the object is upside down. If it was positive 6, it would have kind of same position, but it would have been here, but it's not. And 6 meters matches the height that we kind of got here. That's why there's 1 meter per grid space. And lastly, the magnification. We can just choose any. We have all 4 quantities that we could use. Let's just go H prime over H. That's minus 6 meters divided by 2 meters. So the magnification is minus 3. So the minus means the image gets inverted 3 times bigger. So I think this all agrees. Hopefully that's clear. Let me know if it's not. Otherwise, we'll press onward. Oh, there was a comment in the chat. Yeah, so I did go pretty quickly on the magnification, so we can go over that. Okay, so the interpretation. Yeah, so the minus 3, let's connect this to the drawing we have here. Yeah, so the minus, maybe we can just make some notes. That'll at least be a good start to. So it means the image is inverted. So the magnification is always asking, it's kind of like a relationship that describes what the image looked like in terms of size based on what I started with as my object. And part of the size is it right side up, is it upside down? So this is 3 times larger. So let's actually compare what we have inverted and 3 times larger. That's what I'm saying minus 3 is interpreted as. So let's go back to drawing. So notice here that an object that was 2 meters tall, 2 units on our grid space is high. This one is 3 times larger. We which is a good 6 meters, right? So it's clearly 3 times bigger. But if you look at where the arrowhead is and where it points, it's pointing downwards. The entire or image is below the x-axis. We have the entire image above the x-axis. So it's gotten 3 times bigger. It's also been flipped. So that's the interpretation of -3. And I'm just calculating this. You could get the exact same result if you used this equation as well. But I think the ratio of the heights for something that's magnification is a little bit more intuitive. Cool. I'm glad you asked. Thanks. Okay, so this is a question on refraction. So mostly geometry and Snell's law, which I think is going to be a common theme for most refraction problems, honestly. So hopefully you guys are comfortable adding angles up to 90 and 180 and that kind of stuff. That's most of the complicated stuff. Okay, so we're told that we have a light ray. It's in air, and we're denoting the index of refraction of air as 1, which is a really fine, it's a good approximation to make. It's very useful and makes all these problems easier. It's incident with an angle of theta on an isosceles prism. So one thing to note, and I'm sure you guys went over it in lecture, but good to keep in mind, this angle theta, any angles of incidence and all this kind of stuff, they are always measured, or almost always measured with respect to the normal. If they're not measured with respect to the normal, it's because whoever designed the question is probably trying to make you work harder, and you have to calculate what the angle is with respect to the normal. So you can obviously, everything's in black. It'd be nice if there are different colors. Maybe I'll switch to red. We have the side of the triangle here on the left side, and this dashed red line is perpendicular to the surface of this prism. This angle here is 90. So when finding out what theta is, I mean, it's clearly labeled here, but it's helpful if you have to ever figure this out on your own and draw in your own angles. So you take the angle, or sorry, the normal here, this dashed line that I've traced over in red, in blue here, which I might erase in a second, but in blue, this is the incident ray, it's the solid line. The angle between these two is the angle of incidence. Similarly, this angle here, which I will label as something in a second, that would be our refracted angle. We always care about the angles in refraction problems between the ray of light and the normal to the surface, so the perpendicular line to the surface. Okay, back to what the question is getting at in the details here. So we have this angle theta on an isosceles prism. So this is the angle the light is incident at. The isosceles prism, remember that isosceles, what that might mean in terms of number of sides that are equal, number of angles that are equal. It has a vertex angle of phi. That phi is labeled up here. The angle of incidence is chosen so that the ray also exits at the same angle. So we have the same theta on the left side. And if you look at its original trajectory, which is this dotted line here to the right, the resultant beam is deflected by some angle beta. That's the amount it's changed path from the original trajectory. Are asked to find what the index of refraction of this prism is if we're given a couple of the angles. So phi is 70, beta is 50. So basically the way to go about this is we need to start labeling some angles, and we want to find relationships between the quantities that we know. So we know what phi is and we know what beta is. We have the index of refraction of air. So we want to find some relationships that will allow us to use Snell's law. Which will be n sine theta is equal to, or n air times sine theta, where theta is this angle here, is equal to n. We'll even call this n prism. Actually, I don't want to write that out a bunch, so we're just going to call that n. And it's even labeled right here. So n is the index of refraction of the prism times sine. Let's give this a Greek letter. I'm going to call this delta. Okay, sine delta, lowercase delta. So if we can solve this equation, we can figure out what n is. To do this, we need to figure out what theta is, and we need to figure out what this delta that I just labeled is. And that's basically all through geometry. So we just need to play around with this and start labeling angles and figuring out what is what. Okay, so trying to think of the easiest way to go about this. So this is an isosceles triangle that we're looking at here. It's a prism, but we're looking at the cross section. So we did an isosceles triangle. What this means is this side and this side are the same length, and these two are the same angles. Alex is asking, beta is the angle between the two dotted lines. Yeah, exactly. So the way to think of beta is that imagine that this incident ray right here kept on going forever. It didn't get refracted at all by the prism. So consider that to be like your reference line. And then given that in reality, the line actually does get refracted, when you extend these lines back to where they meet, what is this angle in here? That's beta. So I think based on your description in the chat, I think you understand um, what beta means. Yeah, so this is a nice isosceles triangle. What this means is if this angle here is equal to 70 degrees, we know that all the angles in a triangle have to equal 180. And if we call this, I'll just call this x and this one x because they're the same. We know that the outer angle is this phi. I could leave it as phi, I guess. That's probably better. Phi plus 2x has to equal 180. Those are the three angles in this massive, the outer triangle that we're dealing with. So we know that phi is 70. We want to find out what this angle is. There's two of them. 110 divided by 2 is equal to x, which means it's equal to 55 degrees. So I'm just going to replace this, sub in 55. We might get too many variables if I try and find unique ones throughout. This is 55. And this here, these are also 55. Notice that we have a similar triangle in here. It's the exact same angles as the outer kind of big equilateral triangle. So this huge, not the huge, the angle is kind of divided into dotted lines. This is also 55 degrees. So I think, I'm not guaranteeing this is going to be super messy, but it might, or I can keep this really tidy. Okay. What do we want to do next? Okay, let's look at this triangle on the right-hand side here that has beta. So beta is this angle here that we kind of had that question about a second ago. This is a 90-degree angle. And I'm going to call this little piece in here, let's call that alpha. We don't really need to worry about the names, but anyways. So there's 180 degrees in that triangle. The three angles we have are a 90. We have beta, and we have this alpha that I just named. So we move the 90 over to the left-hand side. That means there's 90 left. It has to be distributed between beta and alpha. Beta is equal to 50, the problem. So that means that it has to be equal to 40 degrees. Is that accurate? No, I feel like I did something wrong there. Yeah, I definitely did something wrong there. Maybe someone in the chat spotted what I did. How do I know that angle is 90? Maybe it's not a 90. That's probably what I did wrong because 40 looks really wrong to me. Oh yeah, okay, I know what I did wrong. Yeah. Okay, so I got ahead of myself moving into this triangle. Let's ignore this, ignore this. I liked the red, so we'll stick with that. Okay, so we have an angle here. This is a straight line. The assumption of making this a right angle, probably not the greatest. So this angle in here is going to be 180 minus beta. Because this is a straight line here, beta is the first angle, this piece that's remaining is the second angle. So 180 minus beta is equal to 180 minus 50. That means that this so-called 180 minus beta that I haven't given it a proper variable name, that's equal to 130. Now let's call this alpha. This is what I wanted to call alpha. So we have this new triangle. I'm going to kind of work with this one in here. The three angles we have are that 130 that we just calculated, plus we have two alphas. That means we have 50 is equal to 2 alpha, or alpha is equal to 25. So this is 25. So now we're starting to get somewhere. So if we can replace this if we want, it doesn't really matter. This is 25, this is 25. Now this is where we can figure out what this angle in here is. This total is 55 here. This must be 30. This must also be 30 by symmetry. I think if you guys figure it out, I don't think we're gonna have to figure out what this angle is, but you will find that it was indeed not 90, which is why that momentarily caused a problem for us. But now we're kind of getting to where we need to be because we want to figure out what this delta was. Our goal from the start. So one thing that we can guarantee is that this dotted line, right? This is the normal to the surface of the prism. So this angle in here, try and do this tidally, this is a right angle. So this angle that has 1, 2, 3 pieces, these all add up to 90 because they're in between, they kind of comprise the space between this dotted line and the edge of the prism. So this right angle is equal to the sum of delta plus that 30 degrees that we figured out plus the 25 that we figured out. So 90 minus 30 minus 25 is equal to delta. So 90 minus 30 is 60. Minus 25 is 60 minus 25 is 35. So we have the first piece, and it seems like we had to work really hard for that, but it's kind of just how it is. And we're going to have the second piece, theta. It's going to fall into our lap pretty easily. Okay, so I'm going to erase a little bit of this just to try and, yeah, I'm going to try and tidy this up a little bit so we can make sense of what I'm going to draw next. Okay, this is good. Okay, so notice that just based on the geometry, not the rays or any kind of physics that's going on, just the geometry, we have an X right here. Kind of between the two lines. So on the left-hand side of the X, we have this angle here. This is what we called theta. This has to be the exact same angle right here. So theta is equal to 25 degrees plus delta. We found that delta was 30 degrees, so that tells us that theta has to be equal to 60 degrees. And now we're set. I think we have everything we need for Snell's law. This was 1. The index of refraction of error is pretty much always 1. We want to solve for the index of refraction. So the index of refraction is just equal to sine theta divided by sine delta. We know what real numbers for those are. So that's sine of 60 degrees divided by the sine of 35 degrees. And you plug that into your calculator, should get something like 1.51, which is a totally reasonable number for an index of refraction. You'll find that they're 1.2, 1.5, something like that for most kind of normal glass type materials. So, momentary hiccup there. I think we kind of brought it back together. You guys can see it's just a lot of fiddling about, and we could have worked a little bit less efficiently. We could find every single angle in this schematic. Usually it's just gaining familiarity with these problems and finding kind of a quick way to angles that are really helpful and critical to you, often by leveraging the symmetries in the problem. Okay, so this is our last question here. So Alex said not almost instantly get the 35-degree angle for delta. I'll check what you mean, but without checking ahead of time, yeah, you're probably right. Let me see what you said again. Since we know the bottom angle is 55 degrees. Yeah, I think you probably could. Yeah, so there you go. Yeah, no, I totally agree. So there you go. Maybe Alex should host tutorials from now on. Make my life a little bit easier. Yeah, no, I totally agree. So I guess it shows you all roads lead to Rome, so some are just a bit faster than others. Okay, so we have another problem that has refraction, a different shaped prism. Procedure is going to be exactly the same. Hopefully not exactly the same. Hopefully I get the most efficient way of doing this, not Alex, but he's probably going to be undefeated, I bet. So for this one, we are given the index of refraction of the prism this time. We have two refractions again, and the unique thing is right here. The second refraction, kind of as the beam is exiting the prism, it exits exactly parallel to the face. So this is kind of the threshold for total internal reflection. You're just at you've just achieved it. This is a critical angle for the second refraction. We know that, like I said, n is equal to 1.5. We're asked this time for what the angle of incidence is in degrees. And we assume that air has an index of refraction of 1, as pretty much always. So this is a case where for this second refraction, generally when you have total internal reflection, or if you have something where there's like a critical angle, it's good to work backwards from there because you kind of get some parameters almost immediately. But we have to draw for this. We have to draw in our own normal. So I'm gonna do that in red here. And I think that's something that a lot of students struggle with. Like obviously my drawing is trash, but the angle that I chose to draw it at is pretty decent. So you got to make sure that you're perpendicular to the surface. I know some people I know a lot of people like to try and live on an XY axis, something like this, where things are vertical or horizontal perfectly, and I think that's hard to shake sometimes. But this is the angle that the outgoing ray is refracted at. It's 90 degrees. We've drawn this angle between the normal and where the ray went. This kind of incident angle that happened at the critical angle here. Again, you draw that between where the incident ray is and the normal. So if you said this was the critical angle, that would unfortunately be incorrect. It's this one over here. And if we want, we don't have to, but we can immediately solve for this, right? We have this n. So n is kind of where the beam is incident. It's inside the prism. It's at the critical angle. It goes out into air at some refracted angle, but that angle is 90. So this is 1, this is 1. And what we find is that the critical angle is just equal to the arc sine of 1 over n. I didn't actually compute that, so we can backwards and do it kind of the way I have in my notes here. It's not really that big a deal one way or another. So this, but we're gonna have to go through the same steps that I will go through now, and hopefully get us to beta, which is where we want to be, because beta is what we're solving for. Okay, so here things are pretty convenient. We have a 90-degree angle. We have a 90-degree angle here. We have a similar situation where you kind of have, if you do look at the triangle kind of made by the vertical side, dashed line, and then the hypotenuse here. It's a similar triangle to kind of the overall shape of the prism. We have a 30-degree angle, a 90-degree angle. Hopefully, you guys are familiar with certain special angles. So this is 30, 60, 90 triangle. And if you're not familiar, you can just figure out what 30 and 90 add to. That has to go into 180. You'll find that it's 60 degrees. This one down here is also 60 degrees. Lots of different ways you proceed. You can list this as 120 if you want. Now, this quantity in here would be 90 minus the critical angle. Now we have, let's call this, what do I want to call this? I'll call this alpha. Alpha is the angle of refraction for the refraction that occurred with beta as the incident angle. So this is getting to where we want to be. So what I mean by where we solve this form of Snell's law, something like this. So I think all we need to figure this, we have everything in this triangle, so 180 is equal to 120, so 60 plus 90 degrees minus the critical angle plus alpha. I think if you do take this guy, plug this into here, and you do the algebra, you will find that alpha is equal to 11.8. So not a nice number, but attainable nonetheless. Then at this point, all we need to plug into our Snell's law that we wrote down here. The index of refraction of air is 1. We had the prism, and we had the sine of our angle alpha. We want to solve for beta, so we just want the arc sine of what we had on the right side. That's 1.5 times sine of 11.81 degrees. And just a reminder, I mean, this is super duper simple and hopefully not a problem for any of you guys, but reminder that with this is a unit that's very heavy in kind of trigonometric functions. If your calculator is not in units of degrees, you will almost certainly get a wrong answer majority of the time. So if you're running into a lot of problems on your Kappa, maybe that's a very simple solution why. If you plug this guy into your calculator, you'll get 17.88 degrees, I believe, hopefully. So I think that's all I have for you guys tonight. We're done maybe 15 minutes early, which I think is to be expected. Thanks to everyone who participated in the chat, and thanks for Alex, kind of bonus points, bonus make-believe points, because we don't get points for being here, but for having a quicker solution for the problem 2. If there's anything fuzzy or anything on any of these problems, let me know before we all sign off.